hopping over to section 3, looking at the shapes of molecules and polyatomic ions. And our learning goal is to be able to predict the three-dimensional structure of a molecule or a polyatomic ion. The valence shell electron pair repulsion theory is also called VSEPR. The three-dimensional shape of a molecule or a polyatomic ion is determined by drawing its Lewis structure, which you should feel comfortable with at this point, and identifying the number of electron groups, or one or more electron pairs, around the central atom. We count lone pairs of electrons, single, double, and triple bonds as one electron group. So you can also look at it and go, well, how many things are around my central atom? In this picture, there's 1, 2, 3 things around this central atom. It doesn't matter that this is a double bond. It still counts as one thing. So how many domains is another thing that we can call it. In the VSEPR theory, the electron groups are arranged as far apart as possible around the central atom. We count lone pairs of electrons, single, double, and triple bonds as one electron group. Once we count the electron groups that surround the central atom, we can determine its specific shape from the number of atoms bonded to the central atom. In the Lewis structure CO2, there are 2 electron groups, 2 double bonds, attached to the central atom. If we look at this central atom down here, there is 1, 2 things or 2 domains coming off of the central atom. According to the VSEPR theory, minimal repulsion occurs when 2 electron groups are on opposite sides of the central atom. They are repelling each other. They want to be as far apart from each other as possible, which makes this a linear electron group geometry, and it gives us a shape that's linear with a bond angle of 180 degrees. In the Lewis structure for formaldehyde, H2CO, the central atom is carbon, and it is attached to 2 hydrogen atoms by single bonds and to the oxygen atom by a double bond. Minimal repulsion occurs when 3 electron groups are as far apart as possible, which gives us 120 degree bond angles. This is called trigonal planar geometry. With 3 bonded atoms, the shape is trigonal planar. Central atoms that have 3 electron groups, a single bond, a double bond, a lone pair, such as SO2, have a trigonal planar electron group geometry. Why? Even though this doesn't look like there's 3 things attached to it, let's look at our electron dot diagram. There is 1, 2, 3 things coming off of that S. We cannot forget about the lone pairs of electrons. 1, 2, 3. So it has an electron geometry of trigonal planar because there are 3 things coming off of that central atom. But then we have to look at how many atoms are coming off of it. And there's 1, 2 atoms coming off of it and 1 lone pair. So because there's 2 atoms and 1 lone pair, it's a bent molecule. And I'm going to give you a cheat sheet here in just a minute, but let's look at a couple more examples. Methane, CH4, here's our Lewis structure for it. We did this earlier. The central atom is bonded to 4 atoms. This is called a tetrahedral. That gives us minimal repulsion of all those hydrogens. Our bond angle is 109 degrees. When there are 4 atoms attached to 4 electron groups, it is called a tetrahedral. It not only has a tetrahedral electron geometry, it also has a tetrahedral shape because there's 4 things coming off of it and 4 atoms. Let's look at NH3. My electron geometry here, based on my Lewis structure, I have 1, 2, 3, 4 things coming off of that nitrogen, just like I had 4 things coming out of this carbon, but the difference is I have 3 H's and 1 lone pair. So our electron geometry is tetrahedral because there's 4 things coming out of it. But because there's 3 atoms and the lone pair is up here, we don't count the lone pair when we're looking at the actual shape that it makes. We have what's called trigonal pyramidal. Let's look at another example where there's, again, 4 things coming out of our central atom. So it has an electron geometry of a tetrahedral. In this case, though, there's 2 hydrogens coming off of that O and 2 sets of lone pairs. So there's 4 things off of my central atom, giving me an electron geometry of tetrahedral. But only 2 of the things coming out of that oxygen are atoms. That gives us a bent shape. Here's our little cheat sheet. If there are two things coming out of that central atom, its electron geometry is linear, and of those two things coming out of that central atom, if two of them were bonded atoms and there was no lone pairs, then we would have a linear shape as well. An example, CO2. We already looked at CO2. Now the next part is if I have three things coming off of my central atom, and the electron geometry, if there are three things coming out of it, is a trigonal planar. Now see where the difference is right here. If those three things coming off of that central atom were all three atoms, then my shape is trigonal planar. If of those three things coming off of my central atom, there was two atoms and one lone pair, then I have a bent structure. And here are two examples of that. There's 1, 2, 3 atoms, no lone pairs. So it's trigonal planar. This is 1, 2 atoms, and there would be a lone pair up here. That's what the third piece is. So this is a bent molecule. Then we have down here 4 things coming off of my central atoms. So the electron geometry is tetrahedral for all of those. But then where the difference comes in is looking at how many atoms and how many lone pairs. This is 4 atoms and no lone pairs. So it'd be a tetrahedral. That's where these would be the same. This is if of those 4 things, 3 of them are atoms and 1 of them is a lone pair. Then I have a trigonal pyramidal shape. And of the 4 things coming out of the central atom, 2 are atoms and 2 are lone pairs. So that would be a bent structure. Those all go together, these go together. And here are examples of each of those tetrahedrals. Let's do a sample problem. Use Vesper theory to predict the shape of SiCl4. Pause here. Here's silicon. It has 4 outermost electrons. And chlorine, we know, has 7. Let's draw our Lewis structure. Silicon, there's only 1 of them, so it's going to be our central atom. And we know that there will be 4 chlorines. So I'm just going to spread out the chlorines around the silicon. And let's do our electron count. 4 for silicon plus 4 times 7 is 28. So that's 32 electrons we need to draw. Let's get started. We know there's at least going to be 1 bond between all of these guys. And then we have all of the lone pairs of electrons around chlorine. So that would be 2, 4, 6, 8. Let's do 8, 16, 24, 32. If I counted all of these electrons drawn around there, there should be 32 electrons. The next thing we need to ask ourselves is, how many things are around silicon? There's 1, 2, 3, 4 things around silicon. So I'm going to go back to that last cheat sheet, and 4 things around our central atom would be these 3 options. So it's a tetrahedral electron geometry. Now, of those 4 things, how many atoms are there and how many lone pairs are there? In ours, we have 1, 2, 3, 4 atoms and no lone pairs. So our 3-dimensional shape will be a tetrahedral shape and will look like this. Take a minute to look over the review for this section.